Hello students, and welcome to section 8-5, linear, exponential, and quadratic models. So how can you determine whether a linear, exponential, or quadratic function best models data? Example 1. Determine which function type represents data. So for part A, it says how can you determine whether the data in the table can be modeled by a linear function? So what we'll do here is we'll take a look at some data. First, confirm that the differences in the x values are constant, which we're about to see possibly take shape. Then, analyze what we call the first differences. So here we go, our xy table, and then of course on the far right side you see first differences. First differences are actually the differences between consecutive y values, and you'll see that take shape as follows. So if we take a look, the very first two ordered pairs, we've got -2, -1, and then we have -2, +1. The consistency from one x to the next is that you're adding 1 every single time, and we can see that. And as far as any consistency, if it even exists, on the other side we can actually see, maybe you can already denote that we're simply adding 2. -1 minus a -1 is simply 2. So -1 plus 2, 1 plus 2, and then you see 3, and so on and so forth. So I do want to make a correction. This is plus and this is plus. So we're adding 1 to every x, and we're adding 2 to every y. And as you can see, the rest of the table takes shape as such. Okay, so please note, again, confirming that, again, adding the same consistent value to x, and then of course adding that consistent value to y throughout the process speaks to the following. A linear function then best models the data when the first differences are constant. First differences are all the same. So if we did write a linear equation for this, it would take the form of y equals mx plus b. And that might be something we take a look at more in depth later. That's a nice warm-up for today. Moving forward, part B. How can you determine whether the data in the table can be modeled by a quadratic? And I've actually denoted off to the right here what a quadratic entails, at least the standard form. If you recall, y equals ax squared plus bx plus c. So let's take a look. We'll go ahead and take a look at our table, and not just the first difference, we'll also be taking a look at the second difference. So analyze the second differences. So here we go, x and y, first differences again, but then second differences. So if we take a look, 0, 3, I haven't yet, of course, deciphered a first difference because you need at least 2 points, and there you have it. You can find that the first difference, 9 minus 3 is 6, continuing. 19 minus 9 is 10, but now you can actually do the second difference. In other words, you can take 10 minus 6 to get 4. And so on and so forth. The first difference with the next two ordered pairs, 14 minus 10, or pardon, 33 minus 19, which is 14, but of course 14 minus 10, as you see in the next table there, or the next column, the second difference is established as, again, 4. And so on and so forth. If we continue, we have the difference of which is 18, and then 18 minus 4, again, is 4. So the first differences are not constant, so we need to check the second differences, which is why we have this column. The differences between consecutive first differences are the same, and those are called your second differences. So that's the gist here in terms of what we're going to essentially justify as the best model. A quadratic function best models the data when the second differences are constant. All of these numbers are the same, so y equals ax squared plus bx plus c would be the best model. Part C, how can you determine whether the data in the table can be modeled by an exponential function? So I have actually denoted off to the right again what we've already discussed, y equals mx plus b from example 1, particularly 1a, I believe, when we talked about, again, this one. Y equals mx plus b is certainly a final answer that would make sense in context, but so would this, an arithmetic sequence setup. What we're about to take a look at, however, in comparing arithmetic and geometric sequences is possibly this. Okay, and I am going to describe that again as they describe with an exponential function precursor, or at least question to the precursory understanding, such that the first and second differences will not be the same or constant. Find and analyze the ratios of consecutive y values. So here's your tables. Okay, we've got x, y, first and second differences, but then we also see there the column entitled ratios of y values. Let's continue. We've got 0, 1. Of course, you need 2 points for a first difference. You need 3 points for a second difference. Okay, you can already start to see that these numbers are not the same. And if we continue, these numbers are not the same. So the first differences are not the same. The second differences are not the same. So we know it's not arithmetic. We also know it's not quadratic. So hopefully, and as you can already kind of tell here, of course, the ratios are the same. In other words, 2 divided by 1 is 2. 4 divided by 2 is 2. 8 divided by 4 is 2, and so on and so forth. Again, first and second difference is not constant, while the ratio or ratios of the y values are all the same. What does that tell you? Well, again, it's not arithmetic and it's not geometric. It's not arithmetic nor quadratic. It is, however, geometric. The ratios of consecutive y values are the same. Geometric technically is the same as exponential, which we'll take a look at as they describe here. At least an exponential function best models the data when the ratios of consecutive y values are the same. So if we did model it, it would take the shape of one of these two equations, or both. We could model it after either, actually. So we're going to go ahead and continue. This is going to set the stage for some continued real-world data problems. So let's take a look. Example 2. Choose a function type for real-world data. The owner of a framing store tracks the cost of bubble wrap for packing pictures like the one shown. How can you use the data to estimate the cost of the bubble wrap for a picture with a length of 75 inches? So they've given us a table with length versus cost, inches versus dollars, 6, 12, 18, 24, 30, and then 10 cents, 31 cents, 62 cents, $1.04, and $1.57. So the picture, of course, speaks to setting of the stage for, as you can tell, 75 inches in this dimension. So let's continue with step 1. Determine whether a linear, exponential, or quadratic function best models or represents this data. Analyze at the differences or ratios to determine which model best fits the data. So let's start taking a look. We'll take a look at our table again, but putting it into the context of first and second differences. So same values for x and y. First differences, there we have it with 0.21, 0.31, which are not the same. And look at the second differences already, 0.1, 0.11, 0.11. Now, it turns out that even though the first differences are not constant and the second differences are not identically denoted here, it is roughly constant as they're describing. So we're actually going to use as our best model a quadratic. Quadratic model best represents the data. Okay, the word best implies it's not going to be perfect, but it may be the best thing we can decipher in this context. So let's continue. Step 2, write a quadratic function that represents the data. We have talked about using the graph in Calculator, but also Desmos, using the quadratic regression feature, entering the data as lists, or on Desmos, the XY table as they provided, then using the quadratic regression feature. This is the data that you will find to unfold in doing this analysis. But let's use Desmos to prove this out and in fact get those exact values as well. Okay, so let's take a look at Desmos. If you recall, I did on your calendar create a link to use the specific Desmos calculator that's entitled Quadratic Regression. So please click on that link on your calendar and it should take you to this spot. What you're also going to do once you get there, is you're going to edit the table. Okay, the table should have a set of values already typed in, but you're going to edit because you are going to use the values for this problem. 6, 12, 18, 24, 30, and then as far as the y's, we know 0.1, 0.31, 0.62, 1.04, 1.57. Now these points are taking shape very nicely as such, like we saw in the lesson prior to this. But keep in mind, the red function that also takes shape is technically as close to touching those points as you possibly can get, given the fact that it is a best fit quadratic regression analysis. The r-squared value is exactly 1, which is quite nice. And if you can take a look here, look at your a, b, and c values. You've got, therefore, y equals 0.0014 x squared plus 0.0075 x plus 0.002. Again, this parabola comes very close to touching every single point, but it may not necessarily go through any point for that matter. A best fit regression analysis, of course, speaks to this. So let's take a look. Their analysis, of course, shows this same exact thing. We've used Desmos, not the graphing calculator. And here's the conclusion. Step 3. Substitute x equals 75 into the equation, which you can do. If you are going to be using a different calculator to do this analysis, or if you are just to use Desmos on this analysis, you could, in theory, just scroll on your graph, as I will do actually on the red curve. It's actually easiest to do it this way. And at 75, let's see what we end up with here. So you can see I'm honing in on it, and there you have it. At 75, the red, again, quadratic regression, the best fit model for this, yields 8.942 or $8.94 if we're going to be rounding here. Okay, so in terms of what their analysis takes shape as, they're going to substitute x equals 75. Now there is going to be a discrepancy from what they have compared to what I have. So take a look. I'm going to go ahead and uncover their work. They do use the rounded versions of A, B, and C, which is going to lead to technically not an accurate answer as it could be, or as accurate of an answer as it could be. And as you'll see here, they get 901. My answer was more accurate, and if you recall, I'll just go back to it. All right, we had said that at 75 we had 8.94. They have $9.01. I have $8.94. My answer is more accurate, again, because I'm using the non-rounded decimals. They use the rounded decimals. Are we close? Sure, we are close to $9, but $8.94 is actually more accurate than $9.01. Nonetheless, this is a predicted value. Keep that in mind as you're doing these types of questions. Okay. Example 3, we'll go ahead and get it started. We may have to finish it another time. It does say compare linear, exponential, and quadratic growth. The graph shows population models for 3 cities based on data over a 5-year period. If the populations continue to increase in the same ways, when will the population of city C exceed the populations of the other 2 cities? So I'm going to uncover this and maybe show you that for method 1, you're going to use the table of values, and you kind of see things take shape as follows. Okay, and this will be where we end up. I want you to notice that city A has a linear function, city B has a quadratic function, while city C has an exponential. Notice the XY table of values highlights those respective red, again, line points, blue, quadratic points, and green, exponential points. The population of city C is greater than those of city A and city B. Again, this is just by virtue of graphical and table analysis. I urge, please, that you take a look at the rest of this problem on your own.